Hello, my name is Jacob Buell. This is Lab 3 Circuits with the class of Physics 2212. So the aim of this lab experiment is to show the conservation of energy within a circuit. And so this lab experiment uses the node rule and the loop rule to understand the behavior of circuits containing resistors in series and parallel. And the lab experiment also studies the function of capacitors and resistors in circuits. So for the loop rule, it can be written as the delta V of the round trip of the entire circuit. So adding up the delta V's for each part of the circuit will equal 0. For the node rule, it can be written as the IN equals I out. Current is the same. Then Ohm's law, another important law to know, it can be written as delta V equals I times R. So for an outline of the lab, I conducted an experiment using the online circuit construction kit to explore time-dependent voltage and the current in a DC circuit, and I used the online circuit construction kit to explore RC circuits and time dependence. So for the first part of the experiment about series circuits, the system of the circuit, the surroundings are everything else. And in the picture you can see the circuit here. There are a couple assumptions. The resistance of the wires and the ammeter is negligible. And the goal is to determine the current flowing through the circuit using the loop rule. So we have two 1.5 volt batteries, two ammeters, and two resistors, each 147 ohms. So R is just the combination of the two resistors, 147. I is V over R, which is 0.02 amps. Now, if you have one ammeter and you replace it with a voltmeter, then the V is going to be 3 and I is 0 amps. Now, another thing to know is if the circuit is open, there's going to be no current as opposed to being closed. Now, for the potential difference for each part of the circuit, on the graph here we have it was given from A to C. And then I drew down the potential difference from C to D, E, F, and G. So AB has 3 volts, and then we get to 0. CD is negative 0.96 volts. EF is negative 2.04 volts, and the rest are 0 volts potential difference. Which this means the delta V of the entire circuit is going to be 0 volts. I will be 0.0204 amps. And the total potential difference, if you add up all the potential differences, it will be 0, which confirms the loop rule. Now, if you connected a 100 ohm resistor with the ammeter, you'll have the current increase to 0.06 amps, the resistance will decrease, and the current increases. And you can see that here in the picture. Now, for the resistance of each circuit element, is kind of self-explanatory. The 47 ohm resistor is going to turn out to be 47. The 100 ohm resistor is turning out to be 100. The wire and the ammeter are both 0. Now for part 2 of the experiment, it's about an RC circuit. We have a 10 ohm bulb, 20 ohm bulb, a 9 volt battery, and then a 200 medium frequency capacitor. So we connected a battery to the bulb and capacitor. The bulb gets brighter, then goes dark, and the current decreases to 0, which means it's charging. If you disconnect the battery, the bulb gets brighter and dark again, and the current decreases to 0, means it's discharging. So for the time, for the 10 and 20 ohm bulbs, it's 9.5 to 19.5 seconds to charge up, and for the discharge, it's around 9.8 to 20 seconds for the 10 and 20 ohm. And then we have a time-dependent model, graphing the natural log of delta V over V naught versus time. You can see the data on the left. The experimental RC turns out to be 6.5 seconds, which the RC is the slope. So the calculated RC is 6 seconds. Conclusion: what if I was doing this lab in real life and I used a real ammeter, then the ammeter would have resistance and therefore contribute to a lower current. Now, if I was doing this lab in real life and used a real battery to charge a capacitor with no resistor in the current, then for the model, the full charge would be reached immediately because there is no resistor to slow down the current. but in real life, the wires would cause a resistance and make the capacitor charge slower.